Welcome. This is the fourth in the series of videos I've entitled Understanding Space Weather. And this is about the rotation of the Sun. In the first few videos we looked at the Sun as a star, what was going on inside the star, and how the Sun gets its energy. Now we're going to look at the consequence of the fact that the Sun rotates. And it turns out that the Sun would be a much less interesting star without that rotation. It comes as a surprise to many people that in fact the Sun does rotate. But it doesn't rotate as a solid body because it's a fluid. So some parts of the Sun rotate faster than other parts. At the equator the Sun rotates once every 24 days. At the poles it's once every 35 days. And you can determine this by either following features across the surface of the Sun or using spectroscopy. You can look for the Doppler shift in spectral lines from the solar spectrum. You can see from the lines on the eastern side of the Sun that the plasma is coming towards you, and on the western side that it's going away from you. So on the east it's blue shifted, on the west it's red shifted, and you can measure that velocity at about 2 kilometers per second. Let's take a look at a video of the Sun rotating. This video encapsulates about 28 days of solar rotation. Now you can see the sunspots rotating from east to west across the image. When you look up the solar rotation rate, you may find a number of different values. That's because there's two different types of rotation that are often quoted. In the bottom left here we have the Sun with a sunspot on it, that's the yellow disk, lined up with the Earth and a distant star. Now 24 days later that spot will be back aligned with the distant star. However, the Earth has moved further around in its orbit, so as far as the Earth is concerned, the Sun has not completed its first rotation. That takes yet another 2 days. So there's a 24-day period which is called the sidereal rate, and there's a 26-day period which is the synodic or Earth-based rotation rate. As I said, the higher the latitude on the Sun, the slower the Sun rotates. So the equator is moving faster than the poles, and in the intermediate latitudes are moving at some rate between those two values. Now the Sun has a magnetic field embedded in the plasma that is churning around in the Sun, and so when these different rotation rates act on that magnetic field, it gets wound up, and as it gets wound up it gets stronger. And that's very, very important because that actually creates things like sunspots. Now because of this twisting and strengthening, you can store energy in a magnetic field. It's rather like a rubber band. You know, if you take a rubber band and start twisting it, it will store energy. You could actually use rubber bands to power a propeller on an aeroplane, for example, a model aeroplane. But if you over twist it, the rubber band will kink. It's called a kink instability. And that kink is very, very important to the Sun because that makes the twisted magnetic fields beneath the surface of the Sun pop through the surface of the Sun, and that creates sunspots. Sunspots are merely places where the strong magnetic field from below the surface of the Sun is poking through the surface of the Sun. Now if you keep on twisting the rubber band or break it, or you accidentally break it in some way, all that energy is suddenly released, and that's what causes flares. Exactly that. The magnetic field gets twisted up to its breaking point or interacts with other magnetic fields and breaks, and all the energy that's stored in that magnetic field is released in the form of a flare. This wrapping of the solar magnetic field explains a lot of the strange features about sunspots. For example, that the leading spot in each hemisphere has the same polarity. If you look at the direction at which these field lines are wrapped, they're always slanting the same way towards the equator of the Sun. So you'd in this picture you'd have north as the leading spot and south as the trailing spot, no matter which of these field lines kinks. Similarly, in the southern hemisphere the tilt is the opposite way. So in the southern hemisphere the leading spot would always be south and the trailing spot always be north. So you have different polarities for the sunspot groups in the two hemispheres. This also explains why in most cases the leading spot in a major sunspot group is closer to the equator than the trailing spot, because again of this wrapping leaves the field lines tilted towards the equator. So we've discovered that the surface rotates differentially, i.e. at different rates at different latitudes. However, if you go down deeper into the Sun, you find there's also differential rotation as a function of the radius of the Sun. So the deeper you go down, the slower the Sun rotates. This also causes a twisting and churning of the magnetic fields, and is actually one of the explanations for the solar cycle, as we will see in a later video. So this concept of rotation is very important. The rotation of the Sun explains the presence of magnetic fields on the Sun. It also explains sunspots, solar activity, the flares and coronal mass ejections for example, and the solar cycle itself. So the fact that a star rotates is very important. The faster a star rotates, generally the more active it is. The slower a star rotates, the less active it is. In the next video we're going to discuss sunspots. Why are they cool? How big can they get? And how do they affect us? So until next time, stay safe